Got a couple more small topics to finish before the end of the unit, and I'd like to finish them both today. Preparation for our unit test on Monday. We're going to talk about the generator effect right now, which is the opposite of what we've just been doing. What we've just been doing is sometimes called the motor effect. It involves a wire with an electric current going through it exposed to an external magnetic field. There's a magnetic force on that wire, and that causes the wire to move. If that wire is oriented and hooked up properly, then we can cause something to spin and we get an electric motor. Okay, whether it's spinning or not, we often call it the motor effect. Okay, bottom line is the motor effect is when electricity in a magnetic field causes a magnetic force. Listen carefully to that again. When electricity in a magnetic field causes a force. Got it? Okay, picture it. Okay, you got a wire with a current going through it. It's in a magnetic field that causes a force. What's the generator effect? It's the exact opposite to the motor effect. Instead of electricity in a magnetic field causing a force, it's a force in a magnetic field causing electricity. With the generator effect, we're generating electricity from magnetism. Generating electricity from magnetism. And we're doing that by applying a force, and we'll talk a little bit more about that in a minute. Sometimes we call it the generator effect. Electromagnetic induction. It was discovered independently by two guys around the same time. A guy named Michael Faraday, who was an American, and Joseph Henry, who was a British guy. Look at the time frame here. Remember Ørsted's discovery, the first discovery of electricity and magnetism, the relationship between the two. Electricity causes magnetism. Okay, that was 1819. That was 12 years before this. Okay, 12 years before, only 12 years before, we discovered that electricity generates magnetism. 12 years later, we discover, hey, look, magnetism generates electricity. Sometimes. So how do you accomplish it? How do you generate electricity from magnetism? If I said it only happens sometimes, then we got to know when that sometime is. Well, remember what I said a few minutes ago. I said that the generator effect is the opposite in the sense of the motor effect. In the motor effect, you've got electricity in a magnetic field, which causes a force on the wire. Here, we're applying a force on the wire in a magnetic field, which is going to generate an electric current. So we're going from, in the motor effect, the electric current in a magnetic field to a force. In the generator effect, we're going from a force on the wire generating an electric current. So here's how we do it. We move a wire. We move a wire in the magnetic field. Now we can do that in a number of ways. We can physically push the wire in the magnetic field. We can have the wire set up in such a way that water falling over a waterfall will turn a turbine, which moves wire in a magnetic field. We can, when as a kid, I remember now you get a light on your bike now, and that light is battery powered. It's usually LED lights that are battery powered. When I was a kid, I had a light on my bike, but when I was a kid, the lights weren't nearly as efficient as they are now, so the batteries would die incredibly quickly. What they did on these lights when I was a kid is had this little device that would sit touching your front wheel. So this little spinny thing would touch your front wheel, and as you pedaled and your front wheel turned, it would turn this little turbine, which generated electricity. It moved wire through a magnetic field and generated electricity, and that would cause your light bulb to turn on. The downside to that was when you stopped, it stopped too, because you no longer generated electricity. Okay, when you move a wire through a relative to an external magnetic field, you're going to generate an electric current in that wire. Now why? Why do we generate an electric current in that wire? I'll draw a picture of this in a second so that you can see a little bit more detail as to what we're talking about here. But basically it boils down to this. When we move a wire through a magnetic field, there are electrons in that wire. Now you've got moving charges in a magnetic field. You move them, you push them. or the water falling over the waterfall pushed them, or you pedaling on your bike pushed them, or whatever. But whatever it was, we're moving electrons in this magnetic field. And we know when charged particles move in a magnetic field, there's a force on them. So by pushing this wire through the magnetic field, you generate a magnetic force on the electrons in the wire. That causes the electrons to start moving. That's an electric current. Now, if it's part of an electric circuit, a whole circuit, a complete loop, now those electrons will start flowing around and power a light bulb or power whatever it is that you're trying to power, charge a battery. So here's the picture that I want you to look at here. Just take a look at the first one for now. In this first picture, in fact, let's get rid of a lot of the stuff that's in this picture. Okay, let's get rid of the hand. Let's get rid of this. Let's get rid of this. In the end, right now, what do we have? We have two magnets, each with a north pole and a south pole. It causes a magnetic field that points in between those two magnets to the right. And we have a wire in that magnetic field. This wire isn't moving. This wire doesn't have an electric current going through it. It's just a wire sitting in a magnetic field. Right now, nothing happens. Okay, right now, assuming this wire is not ferromagnetic, which usually wire isn't because it's made out of something like copper or aluminum, which is not ferromagnetic, then nothing happens. Watch what happens, though, when I move this wire. I push this wire upwards, or maybe this wire is part of some kind of armature or some kind of turbine in a coal-fired power plant, by which we generate, by the way, something like 70 or 80% of the power in Alberta by burning coal. What happens, how do we do that? We burn coal, produces a lot of heat, right? What do we do with that heat? We boil water. What happens when water boils? It creates steam. What happens to steam? It rises. When the steam rises, it moves wire. It turns a turbine. It pushes wire. And that generates electricity. Same thing happens with nuclear power, by the way. I think nuclear power is this crazy kind of nuclear reaction where we generate electricity from the nuclear reaction. Not at all. With nuclear power, we split the atom. That generates a whole lot of heat, a lot more heat than burning coal does. What does that heat do? It boils water. What does boiling water create? Steam. Steam rises, turns a turbine, same as in a coal-fired power plant, just a lot cleaner. That's all, because you're not releasing all these greenhouse-causing gases with nuclear power plant. Bottom line is, in this case, maybe we got steam rising, causing this wire to be pushed upwards. Maybe we're just physically pushing it upwards with our hands. Doesn't matter. The wire is now moving upwards. Okay, not on its own. Okay, we're making it move upwards from whatever cause. But as it moves upwards, the electrons within that wire also move upward. They have to, right? The electrons are inside the wire. If the wire move upwards, then the electrons inside the wire also have to move upwards. Agree? Let's take out a hand rule for deflection, in fact. Why? Because we got an electron here that's moving in a magnetic field. It's moving because we moved it, but still moving in a magnetic field. We stick our thumb in the direction of the particle, which is upwards, because we pushed it upwards, or the steam pushed it upwards. My fingers go in the direction of the magnetic field, which is from north to south. Palm points which way? Palm points outwards. There's a magnetic force on that electron and on all the other electrons pushing out of the page. So what happens to that electron and all the other electrons? As they experience a magnetic force out of the page, they start moving out of the page. What do we call that when electrons start moving along the length of the wire? It's an electric current. We just generated an electric current by moving. Anybody want to get the wire, right? Make sense? So electromagnetic induction, the opposite, the generator effect, the opposite of the motor effect. Instead of electric current causing movement or force, it's movement or force causing electric current. Right? You got some questions for me to work on page 613. Because I want to do a little demonstration here with the next small topic. I'm not going to have you work on these right now. But you might have a couple minutes at the end of class, I'm not sure. Page 613, number 1 to 3, and 8 to 11. The last thing in this unit that I want to talk about is something that kind of ties the motor effect and the generator effect together. What we've just done with what we've done a day or two. What Lenz's law? We just saw the demonstration where we drop a piece of steel through the copper tube. It accelerates downward at 9.81 meters per second squared. When we drop the magnet, it accelerates downward at a rate of maybe 2 meters per second squared or 1 meters per second squared, dramatically less than 9.81. Why? Copper is not ferromagnetic. It's not going to attract to the magnet whatsoever. It's not going to cause the magnet to stick to the wall of the copper tube. So what happens there? When we drop a magnet through a conductor, we're going to generate a an electric current. Right? That's what we just learned a few minutes ago with Faraday and Henry, right? It's electromagnetic induction. When you move a magnetic field, when you've got a magnetic field and you got a wire, magnetic field and conductor, and you move one of them, you're going to generate a current. So this time we're moving the magnetic field, the magnet, through the wire, through the conductor, we generate an electric current. Nothing new there. We just looked at that a few minutes ago. Okay, that's Faraday and Henry. But that electric current generates a magnetic field. So now we've got Oersted, right, 1819. Learned it way back in this unit. We got a magnetic field causing an electric current, but now we've got an electric current causing a magnetic field. And these are two different magnetic fields. This is the original, this is the new magnetic field. It was generated by the current that was generated by the first magnetic field. This is Faraday, electromagnetic induction. This is Oersted. Electricity causes magnetism. Now what's important is that those two magnetic fields, B1 and B2, the original one and the one that we just caused, will always act to oppose the motion. We don't say they repel each other. We don't say they attract each other. We say they oppose the motion. They have to oppose the motion, otherwise the law of conservation of energy would be violated. If they didn't oppose the motion, if they helped the motion, then we would end up with more energy at the end than we started with, which of course we know can't happen in any circumstance. Energy would need to have been created from nothing, which violates one of the most fundamental laws that we have. Now, we said it has to oppose the motion, not repel. It says it has to oppose the motion. Let's take a look at this. Let's say we got a coil here. See what I'm doing there, guys? The dotted lines mean in the back, the solid lines are in the front. A little bit different this time. We don't have a battery hooked up to it. Right? It's a light bulb that's hooked up to it. What happens to that light bulb right now? Nothing. You got a wire attached to it. If you don't have a battery attached to it, nothing's going to happen, right? Let's say I got a magnet like this that's going towards it. I got a magnetic field that's moving relative to a wire. What's going to happen? Well, that wire is going to it's going to induce an electric current in that wire, right? And that electric current is going to cause a magnetic field that's going to oppose that motion. We know the polarity of this coil that's produced in it without doing a hand rule. This has got to be north, this has got to be south. Why? Because that's the only thing that's going to oppose the motion of that magnet. If that was south on the right side and north on the left side, it wouldn't oppose the motion, it would help it. We could figure out the direction of the current through this coil now, right? Take out your little crafts that you made a week or so ago here. Magnetic field inside this coil goes from South Pole to North Pole, so it goes towards the right. That means my fingers are going to point up in the front. That means the electric current is going to go up in the front, down in the back. The electric current is going to go around here clockwise. Not because of the battery, but because of the movement of the magnet. I want to show you one more, though. Same setup almost. Coil is set up the same way. Here's the the light bulb. This time, the magnet has gone all the way through, still moving to the left. That's still a moving magnet relative to the wire. We're still going to produce a current in that wire, and that current is still going to produce another magnetic field. And that magnetic field has to oppose the motion. So in order to oppose the motion, what's the polarity got to be? If I'm pulling this permanent magnet away, this end has to be it's got to be north this time, right? Why has it got to be north? Well, up here it was north on this side because it had to repel the motion of this permanent magnet. In order to oppose the motion of the magnet over here, it has to attract it. So opposing the motion doesn't mean repelling. Sometimes opposing the motion means attracting, like it does here, pulling it back towards it. So we got a north pole and south pole reversed here. The direction of the current would be opposite to that. Instead of being up in the front, it would be down in the front, and it would be going other way. Yeah, like this. It would be counterclockwise this time. Got it? Don't forget, guys, you have some check and reflect questions for homework. We also have a little quiz tomorrow, but the quiz is not on this. The quiz is just on basically the F is equal to ILB thing, along with the hand rule for deflection. Right?